the ocular refraction, and then the amounts, and then the object distance, okay? So, and then you do the subtraction, K minus L, then you can get the A, okay? Very easy. And here, because you have introduced an optical device, like a spectacle lens in front of the eye at a position D, so it will make the calculations more interesting, okay? Let me show you with this diagram. Okay, so now you have an object, okay? You have an object at this position, okay? At this position, the distance from the lens surface to the objects is LC. So this is the object distance, okay? Object distance. When you put the objects at this position, and then this is the spectacle lens you have, and after the refractions by the spectacle lens, you will form an image somewhere, okay, depending on whether you're using a positive or negative lens, okay. If you're using a negative lens, then the light will become diverged, and so the image will be forming on this side, okay. So you will have the image form at this position. The LC pi refer to the image distance. So LC is object distance, LC pi is the image distance, okay. If you're using a positive lens, of course, the LC pi will be on this side. The image will be forming on the other side. But if this is a concave lens, then the image will be on the same side. Okay, very likely. And then the second step we need to calculate is the distance. So this image will be now positioned at a distance L in front of the eye. So when you calculate the L, so we have to take into consideration of D. Okay, so with the same, actually with the same objects. Okay, and then with the eye power, the power of the eye, then you can then calculate the accommodations required. Okay, so just by looking at this diagram, you may find this a little bit difficult. So maybe I can show you how the equation is derived. Okay. The first steps, I hope you can still remember. I think this is the first lecture that we talk about, is the effectivity formula. Remember, I have a diagram to show you the relationship between the ocular refraction and the spectacle refraction. I mean the one with the red and blue arrows. Okay, and you can. I hope you can still remember this equation and the other equation here. So they are interchangeable between ocular refraction and the spectacle refraction, I think with a diagram as well. And I ask you, you could either remember the diagram or you could remember the equation, okay? Because somehow you still have to know how to do this interconvention, okay? So because sometimes you have to convert this from FSP to K. I mean, if you want to know more about the contact lens power used, or if you have the ocular refraction, you want to change it back to FSP, then you have to remember this equation. So this is the first part. Second part is that now I present the same figures here, and the first thing you need to determine is the object's vergence as the lens surface. Remember, so the object is positioned at LC pi, sorry, LC, not LC pi, LC in front of the lens, okay, in front of the spectacle lens. So if you want to determine the object's vergence, you simply have to take the reciprocal, because the object is in air, so the refractive index is equal to 1. So you just have to take the reciprocal, then you will get the LC. With the LC, then you can determine the LC pi by using LC plus the spectacle refraction or the spectacle power. Okay. Now you know the LC pi. LC pi, that means the object's vergence. Again, if you take the reciprocal of the image vergence, then you can calculate the small LC pi, which is called the image distance now. Okay, image distance. Okay. So now you know the distance from the lens to the image. Okay, and then the next step we need to do is to find out the L. Why we have to find out L? Remember, so this spectacle lens actually help you to see better at distance. Okay, and that's why you have to use it. I mean, constantly. And the purpose, if you still remember the principle that we talked about, the purpose of you putting this distance spectacle in front of the eye is that it will help you to form an image at the far point of the patient. Because when we can do that, having an image form at the far point, so it will then form an image clear on the retina. So, and that's why now this position represents the far point of the patient. Okay, and that's why we have to calculate the L. Okay, now you see the LC pi. So now we know the LC pi. So calculating the L is not that difficult, because with the LC pi, then you can look at this equation. L is equal to LC pi minus D. Okay, just by looking at this diagram. Or you may say it's just like vector. So L plus D equal to LC pi. Okay, because you have to take the sign convention into consideration as well. So by looking at this diagram, L equal to LC pi minus D. Okay. So when you have this L, of course, then um, you can also substitute this into the equation. Remember, this is LC pi. So this you can substitute into the equation here. Okay. And then if you find a common denominator, then you will be able to get this one. So this looks a little bit complicated now. So L equal to 1 minus D bracket LC plus FSP bracket divided by LC plus FSP. Okay. So this tell you about the far point distance. Okay. So now you know the L. If you take the reciprocal, it will become divergence again. Okay. So the distance and divergence, they are always in a reciprocal relationship. Okay. So that's why you can see that. So now the denominator become the numerator, and the numerator become the denominator. Okay. So this is L. Remember the equations that we talked about at the beginning. A is equal to K minus L. So this represents L, and then the K is from the effectivity formula. Okay. So this is K from the effectivity formula, and this is L, okay, from our calculation. Okay, if you combine the two, okay, I mean, now you can do a little bit work at home, so you can actually work out this relationship. So this equation will tell you amount of the accommodations required at a specific working distance, at a specific working distance from the lens, and also the vertex distance, and also with a specific power of the spectacle. Okay. So you can see this equation is a little bit complicated. However, I think you still need to memorize this equation for sure, because you, in most cases, as I told you before, because most patients will wear spectacle, and that's why we do need to calculate the amounts of accommodations required under different situation. Okay, and if you look at this equation, so you can see people with different refractive error, and looking at the objects at different distance, the accommodations will be totally different. And for patients who are using contact lens instead of spectacle, because when you're using contact lens, D will be equal to 0, because the lens is in direct contact of the eye. So if D is equal to 0, so this part will become 1. This part will also become 1. And that's why A is simply equal to minus LC. So when you're using contact lens, the calculation is a lot easier. Okay, but if you're using spectacle, definitely the vertex distance is also very important. If you change the vertex distance, it will change the amounts of accommodation needed. Okay, so this equation is for you to calculate the ocular accommodations required at different working distance. Okay, LC, as a function of, for example, patients with different refractive error and a different vertex distance. Okay, so I hope you can memorize this formula, and let me show you with some example here. Okay, the first example is very similar to our previous calculation. Okay, so first of all, I just want to show you the two subjects. So one with 5 diopter myopia. This 5 diopter is considered as the spectacle refraction, not the ocular spectacle. The second subject is 5 diopter of hyperopia. Okay, so assuming they have normal accommodation, so and you and have the same vertex distance. So the small d is the same, is 10 mm, also 1 centimeter in front of the eye. And now they have to look at the objects at 25 centimeter in front of the spectacle plane. Okay, so in these situations, can you calculate what would be the accommodations required by uh, the first subjects with 5 diopter of myopia, and also the second subjects with 5 diopter of hyperopia? Okay, so can you do the calculation for these two patients when they're looking at the objects at the same distance in front of the eye with the same vertex distance? So can you calculate whether they have the same amounts of accommodation or not? Okay, so using the equation that I just mentioned. Okay, I will give you maybe like a 5 minute to do this calculation. If you have any questions, just let me know.